I don't know much about ultrasound. I'm outnumbered by experts in the field. But I began these experiments after reading a paper as a graduate student by Francis Crick, Do Dendritic Spines Twitch? And I was, at that point, I was recording from single spines and watching spines twitch, and I became very unsatisfied with the electrochemical description or theories that we have of the brain, and felt that it needed to include mechanics and turned to use ultrasound for a mechanical energy source to study its influence on synapses. And 14 triaged NIH grants later, here I am. I'm going to talk to you today about, for the past 5 years or so, we started studying the effect of ultrasound on synapses, and I kind of took a departure from using optogenetics and multiphoton microscopy into this field, not with the idea of developing brain stimulation devices, but that's where it's taken me. So in the interest of full disclosure, I am a co-founder and the CSO and board member of a company, NeuroTruck Incorporated. It's headquartered in Silicon Valley with R&D labs in Boston, Massachusetts, and next to my academic lab in Roanoke, Virginia. I'm an inventor on 20 plus patents, not including international applications on brain stimulation systems, methods, and devices. So that's out of the way. So now the problem. A problem is really the scale of human proportions, right? We can talk about how to create maps of mice brains or C. elegans, but when we try to translate that to a human, it's fundamentally a different problem. As Rafa mentioned earlier, we don't really know what a neuron or a synapse is a fundamental unit of the brain, but we don't know what a fundamental unit is from a functional standpoint. Is it a collection of 1,000 neurons or 100 neurons or 10 neurons? And it probably depends on exactly what circuit you're studying and the types of behavior you're looking at. But there are very good methods for modulating brain activity now, and we study these in the lab quite extensively. Transcranial direct current stimulation is one. There's other methods, transcranial alternating current stimulation, transcranial magnetic stimulation. The problem, whether it's electrical stimulation or electromagnetic induction of an electric field in the human brain, is the length scale of the electric field is on the order of centimeters. And so the electric field often spans multiple gyri, sulci, and functionally important brain regions. So you can see in these finite element method simulations of electric field distributions in realistic head models, you basically can take up about a third of the cortex using one of these techniques. And so although you can combine them with EEG or fMRI to conduct brain mapping, they suffer from a critical limitation is they have poor spatial resolution. So we began studying the effects of ultrasound on synapses. We first used organotypic slice cultures of hippocampus and whole brain. As Steve mentioned, we did this. This is an example of a synaptophore response. So this is showing us an organotypic slice of hippocampus and showing synaptophore, which is actually probably considered to be one of the first optogenetic probes developed by Jeroen Miesenbach. When I was a postdoc, we made Thy1 synaptophore mice, and so I used those. A couple years later, I actually got a phone call from Bill Newsom, email rather, and he asked me if we could stimulate phosphines, if it would be possible to stimulate phosphines. And so I went to the lab and I piecemealed some stuff together and built these acoustic collimating tubes out of falcon tubes and shrink tubing, and coupled them to the head of a mouse and couldn't get anything to work. We tried lots of things, and then I accidentally hit a button on a function generator, and the mouse had a seizure. And when the mouse had a seizure, I knew that it was possible to stimulate the intact brain with ultrasound, but we just had to dial in the right parameters. And so we published that work in 2 different papers. Therapeutic embodiment, very similar to what Rafa discussed this morning with epilepsy. It's kind of the self-fulfilling prophecy. If you can stimulate the brain, I don't know why the movie's not playing. Let's see here. Well, just let me pull the movie up real quick. Just give me 1 sec. I don't know why it's not playing.
Which button on the function generator did you hit?
I sent it into continuous wave mode, and it actually scared one of the graduate students in the lab. She started screaming. But the mouse was fine. We stimulated that mouse for like 18 hours, and it got up and walked off the table with no problem. So,
Stimulated the graduate student too.
yeah. Well, we weren't doing that at the time, but we are doing that now. Not graduate students, but so I just want to show this quickly. We started using canic acid models of epilepsy, and here what you're going to see is you're going to see a mouse that's having a canic acid induced seizure. It looks pretty well. Just give me a second. Oh, you know what it is? I'm not used to the Mac. Here we go. There we go. Okay, so the mouse will now. All right, let's see if it plays out.
Make it full screen. Then blow it up.
Oh well, the movie's not going to play. You can read the paper. It's in Nature Protocols, and I can show you the movie individually later, just to move on. But basically what we did is we immediately terminated seizure activity in these mice using transcranial ultrasound. And you know, at that point we started to think that it would be really nice to have almost like an automatic external defibrillator for the brain, right? So if someone shows up in the emergency room in status, rather than having someone go make up Valium or other methods to try to stop the seizure, perhaps you could just immediately terminate it with ultrasound. We do a lot of work in swine models in collaboration with Jeff Elias, and this particular example is a non-human primate. I went to Kenya about 3 or 4 weeks ago and recorded from baboons. We went to record from the brainstem and reticular formation, and we actually, here we used a depth electrode and went in between the cerebellum and the brainstem and used a depth electrode to record from reticular formation. And then we had the transducer positioned on top of the head here, going down through the cranium towards the brainstem. And we found that we could indeed modulate deep brain activity in baboons. This is with planar ultrasound. This is not a focused transducer. All that work has been really directed, all the work in swine and the work in non-human primates. Also collaborate with Doris So at Caltech. We work on a macaque model there. All the work has really been to encourage us of the safe use of ultrasound before we started attempting human brain modulation. And so the main question has been for quite some time, can transcranial focused ultrasound modulate human brain activity? And so one of the first things we did, because some of the comments that I've had on grants have been, you can't focus ultrasound through the skull. And I'm like, sure you can focus it through steel that's much thicker through the skull. So you can easily focus it through the skull, and I think we'll hear more about that later. But we created some simple finite element method simulations, and here you can see the diffraction patterns as a function of acoustic frequency. And so this is the skull. This is planar ultrasound, and you can see the diffraction patterns. What we found when we put these models to a test and quantitatively mapped acoustic fields using customized single element focused ultrasound transducers is that the skull actually acts as a lens to ultrasound. It actually focuses the ultrasound slightly, mostly in the axial direction, not so much in the lateral direction. And here you can see the acoustic field maps obtained in free space as well as through hydrated fragments of human cranium. You can also see here, this is basically the beam profile, the lateral beam profile. So this particular frequency of ultrasound that we used was 0.5 megahertz. And the full width half max of the transcranial beam was 4.9 millimeters. And the axial resolution, the half width half max, was 18 millimeters. So we're stimulating about a 4.9 by 18 millimeter area in the brain. Or stimulating modulating activity on that scale. So then we designed an experiment. We thought about different experiments. We designed an experiment where we would target the hand region of primary somatosensory cortex in humans, again using this single element focused transducer. We placed 4 EEG electrodes around the transducer and recorded EEG responses or somatosensory evoked potentials as well as cortical oscillations in response to median nerve stimulation. And then we also assessed the influence of transcranial focused ultrasound targeted to the hand region of somatosensory cortex on somatosensory discrimination behaviors. We projected the acoustic beam into realistic head models, and we found that we were indeed targeting the right area. Here you can see this is about what the acoustic beam looks like. There's two maxima. There's one at the gyral crown, and there's one about 2 centimeters deeper in the tissue. Again, this is with a single element transducer. You can do much better in axial resolution using phased arrays, which I think will be talked about a little bit later. The data showed us that when we applied transcranial focused ultrasound to the somatosensory cortex and elicited somatosensory evoked potentials through median nerve stimulation, we significantly attenuated the short latency activity as well as the late onset activity. And it's been shown quite convincingly that this short latency activity is the primary sensory response, and this later activity is probably due to secondary areas that are involved in cognition or detecting other features of the sensory stimulus. When we look at the event-related spectral perturbation, we also see that there's significant changes in basically alpha, beta, and gamma. But the changes that occur early, right after median nerve stimulation, tend to occur primarily in the gamma band. And so we take this to be that there's probably a change in inhibition in the cortex. We did another experiment to assess the spatial specificity. And as Steve mentioned earlier, ultrasound can be highly specific in terms of its spatial dimensions. And so what we did here is we translated the focused ultrasound transducer 1 centimeter along the anterior-posterior axis from its original location marked by S1. And so when we moved 1 centimeter anterior, we saw that there was basically no effect of ultrasound on somatosensory evoked potentials. Likewise, when we moved 1 centimeter posterior, we also saw there was no effect of ultrasound on the somatosensory evoked potentials, and this was the same case in the event-related spectral perturbation plots. We then devised a method where we used two-point discrimination tasks, which is a common task, psychophysical task, to assess sensory discrimination abilities in humans. And we also used frequency discrimination tasks where we played a series of air puffs to the fingertips and asked the human volunteers to distinguish if the second of two stimuli was different than the first. What we found is that without affecting task attention or response bias, transcranial focused ultrasound significantly enhanced sensory discrimination abilities as assayed by two-point discrimination and frequency discrimination tasks. And so what we think is happening is we're modulating the gamma activity, which is probably causing a change. It's probably reflecting a change in inhibition, which could be leading to sensory discrimination. That's a lot of hand waving, mostly for discussion purposes in a manuscript, which I have no idea why it's really that important, but it is. Putative mechanisms. Again, I began this because I was really interested in kind of mechanical bioeffects and how the brain works from a mechanobiological standpoint. So the brain is a viscoelastic material. It's mechanically sensitive. We all know this. People get concussions. People get knocked out by impact injuries. We've discussed this. We've discussed that it could be a fluid mechanical effect. We have evidence through collaborations where we looked at the effects of ultrasound on membranes in different preparations, primarily Langmuir trough. We use fluorescently labeled phospholipids, and we can do fret microscopy and basically look at changes in membrane tension, as well as conversion to different wave modes in the membrane. We also have been doing single channel recordings from various types of channels, and we've found that we can modulate TREC1 channels, which is a potassium channel that maintains resting membrane potential through a potassium leak current. We're looking at other channels, and in fact, some of the funding that I received from this was from DARPA, and it was to develop an acoustospectroscopic or acoustogenetic method where we would appeal to individual channels or proteins based on intrinsic resonances within the membrane. And we don't know if that's possible or not, but it's something that we've been trying to tackle through these approaches. So the question might be, if you want to activate an L-type calcium channel, would you use one waveform compared to an NMDA receptor, which is also known to be mechanically sensitive? Ongoing in future studies, we have been trying for quite some time to combine transcranial focused ultrasound with bold imaging. Working in the MR environment is extremely challenging We now have transducers that are MR transparent. We are getting some reasonable results, nothing that I would be willing to report on quite yet because we have to continue to work to increase the reliability. But that's what we're working towards, right? It would be really fantastic if we could go in and modulate on a millimeter scale some 3D loci in the human brain and look at connectivity maps. Or if you bring a human in and you do the experiment, intracranial self-stimulation in a human, what would you observe? And other ongoing and future objectives are related to my company. We're really trying to develop bold applications of transcranial focused ultrasound. This is one of our devices that's now being used in human studies at the University of Arizona. We basically reduced it down to a touchscreen 3-pound module that has a single element focused transducer. And I realize it's not as precise as phased arrays would be, but we're not trying to target deep brain regions. And I think on the superficial surface of the cortex, single element transducers work pretty well. The main conclusions are that ultrasound does indeed represent a feasible alternative to other transcranial neuromodulation methods with a resolution on a millimeter scale. I've shown you today data indicating that transcranial focused ultrasound can lead to a significant change in the amplitudes of somatosensory evoked potentials, both early and late activity, as well as cortical oscillations, and that we could modulate sensory discrimination abilities in humans. And lastly, I'd just like to show you this is again, the electric field that's produced via electromagnetic induction with transcranial magnetic stimulation compared to that of transcranial focused ultrasound. And you can see here that transcranial focused ultrasound literally shatters the resolution limits that are obtained by transcranial magnetic stimulation. And with that, I would like to acknowledge many graduate students, postdocs, colleagues who have helped and advised along the way, our funding agencies, DARPA, U.S. Army Research Laboratories, the McKnight Foundation, and my company, Neurotrek. Thanks.
One question, I'm sure there'll be others before I forget. So those human studies where people are doing better on the frequency discrimination test, did you interview with them? What is their experience?
Yeah, so
How do they feel?
it's interesting. So we use some silicone coupling agents, and so we kind of avoid. You can get bone transmission of sound with the pulse repetition frequency. We've avoided those mostly. We published a paper in PLOS One last year where we showed using different waveforms we could activate somatosensory receptors. And so with this particular waveform that we use, the pulse duration is too brief and the pulse repetition frequency is too high to activate sensory receptors.
So I'm not really asking what they physically feel like.
Oh, yeah.
I mean, did they sense it in their minds?
Yeah, no, but
They just,
Stuart
Like-
Hammeroff published a paper, and he's doing work for us now at the University of Arizona. He published a paper in brain stimulation this year, actually. 15 seconds of 2 megahertz ultrasound through the temporal window made him and others, they improved pain rating and they improved mood. People felt better. And I went out to Tucson and I did it myself, and yeah, you feel something.
interesting. Educational applications, something like this, or kids who maybe have learning disabilities at various.
Yeah, so one of the things we're working on in my company, we're not working on medical applications in the company. We do have a DARPA effort where we're working on a return to field diagnostic using tissue pulsatile imaging or shear wave elastography to image structural deficits in the brain combined with neuromodulation. But the main thing we're going after is basically cognitive enhancement.
Right.
So people with learning disabilities or even college students, one of the most popular drugs right now is Adderall. And there's clear evidence in the literature that non-invasive neuromodulation can improve cognitive abilities.
Well, I think your excellent talk stimulated this audience well enough that they would have benefited. Question.
If you're going to apply an artificial stimulus, it's not clear necessarily what the effect would be for you doing the experiment. Should it induce not a sensation? Should it depress it? Right. So are there any animal studies that might guide you? So are there any electrical stimulation where you really know you're putting an electrode on S1 that would suggest an effect that would allow you to interpret whether you're actually excited tissue or anything?
Yeah, so we've thought about that very carefully. We haven't seen anything that really, because we use EEG and the EEG signals are a little bit harder to interpret than extracellular field potentials. But in the EEG literature, there's no a priori assumption that you can make about the amplitude of the potential and the behavior that results, right?
Yeah, but even between stimulation and behavior, if you stimulate S1, do you expect an enhancement?
Yeah. Right. Right, I think it depends on the temporal dynamics, right? How long you stimulate, how hard you stimulate. Because if you stimulate for 100 milliseconds, or you stimulate for 2 seconds, you get. I mean, we know this from LTP and LTP, right? That different types of stimulation paradigms induce different outcomes. So, I think it's a really difficult question. We kind of had our backs against the wall.
So I'm curious about the paradigms that were used by you and Stephen. How similar are they? When you talk about mechanisms, you didn't spend a lot of time talking about the mechanism that Stephen's focused on, which is the facilitation of vesicle fusion.
Right. So quickly on that, so when it could be, and that's what I went after first. I was like, if a spine is tugging on a presynaptic membrane, you get it. And people have known, right, from Chuck Stevens' work and others looking at the red release when sucrose evoked transmitter release, right? That's what we went after. In our paper in PLOS 1 in 2008, we used botulinum toxin. And we use botulinum toxin, we abolished the synaptic forum response, right? And so that's not to say that, I'm sure the retina probably works different, but because you're really appealing to the mechanical properties of the tissue, the retina has different mechanical properties than gray matter versus white matter, right? And I think that's what's really important to understand is when we're talking about the brain, people have started to use elastography and they see structural changes and mechanical changes in the tissue way before the disease occurs, right? And so I don't know why we've been, as neuroscientists, been neglecting these things.
Maybe it would be instead of mechanism, and they're different interpretations.
It's sort of like
In different frequencies, right? Because we want to go through the skull. So the Calero and other people have shown that the mean optimal gain for transcranial transmission and brain absorption of ultrasound is below 0.65 megahertz. And so when you're going through the retina, right, you can get by with, I don't know what the limit is, the upper limit would be. Hundreds of megahertz probably, yeah, right. And so to go through the skull, a thick skull, you want to use lower frequencies.
And the advantage of there being this sort of family of mechanisms that you can tap into might be specificity. You might be able to stimulate populations selectively using different pulse paradigms.
It's possible. We've certainly seen differences in our non-human primate recordings. One thing we've noticed is that you get different responses depending on if a neuron's active or not. And so if a neuron is just kind of ticking away at about 1 hertz or less, you'll tend to stimulate that neuron. But if a neuron is bursting, say if you have a couple hundred milliseconds of like 20 or 30 hertz, then you seem to suppress it with the same waveform, right? So the recent history of the neuron probably plays into this as well.
Let me just make a comment. People, if you're not, the students, people who aren't experts necessarily in what you're hearing, please ask questions, even if they're basic questions, or make comments, because this is a small informal meeting with people of varying expertise. We have experts, of course,
Right.
those questions are great, but I strongly encourage questions from students, postdocs, etc. Yes?
So you were showing EEG effects in humans, but it seems to me that a really direct effect would be to do Bill Newsom's experiment and just get phosphines in humans.
So here's the key. What everyone wants really is they want the transcranial magnetic stimulation motor evoked potential. And I repeatedly said, that's great, right? I'm sure you can induce a motor evoked potential. I tried to induce phosphines on myself and knock myself out, okay? You can heat the skull, and I've repeatedly said, and this is something I said, is like, and maybe I shouldn't say it so coarsely, but I'm speaking truthfully. I don't want to blow up anyone's head on my watch, right? And so what we're doing is we're working with the minimally intensity of ultrasound that we feel like we can reliably achieve effects with, and then we'll start to move up as we validate the safety of those protocols in swine and non-human primates, right? Because you can induce thermal damage and mechanical damage, right? You have to be careful. I would love to be able to get a phosphine. I would love it.
So what are the technical limitations for doing that versus what you've done in humans?
I think knowing how the intensity profiles affect the tissue. It's not, so one thing we did is based on, again, work from Calero showing that if you use a highly focused transducer, you're less likely to get standing waves in the skull, right? Because you're sending sound into a contained cranial vault. And you can get standing waves and cavitation. And people have raised concerns about this. And so I wanted to go forward with the human studies, but do so as carefully as possible. And so, to be honest, we just don't know what the limitations are yet. It's still very early, and I mean, there's a lot of people starting to work on this for different reasons. Work from Jeff Elias, and he had a New England Journal of Medicine paper a few weeks ago, and he showed he was ablating the VIM in the thalamus to treat essential tremor. But when he had the MR guided focused ultrasound or high intensity focused ultrasound, when it was hitting the VPL, which is right next to the VIM, the patients that are awake the whole time, they would get paresthesia in the lip and the finger, and he knew, don't ablate that circuit. So you move the patient, you get to the VIM. When you get to the VIM and you heat up the VIM, you get a termination of the postural tremor, and so then he knew he was in the location to make the ablation, right? And I think those are the things that we're going to start to see that we'll learn the limits, I think.
Yes.
What's the power consumption in the transducer when you achieve a response?
In the transducer,
Yeah.
so we're putting about a couple hundred volts into the transducer. It's about 50 watts. So it's the transducers are, and I think Pierre can speak to this. The transducers are incredibly inefficient. A lot of them are. Some of them heat up, you know, and so it's like, but a lot of the ultrasound transducers, at least the ones I've worked with, you have to use really high power to be able to drive them, you know, because we're sending about 40 watts across the skull.
So do you see a need for development of new transducers?
Absolutely, absolutely. We've always felt that there's probably, you know, you can expand the bandwidth because high intensity transducers typically have low bandwidth, broadband transducers low power. So and you know, in some of my early work, I kind of, and I don't know if I'm correct or not, but I kind of always felt like the broader the bandwidth, the more reliable the response you would obtain. And so I think, yeah, developing transducers is definitely going to be a part of this. And as I mentioned, you know, using acoustic metamaterials will be a part of this. There was a paper not too long ago from Spadoni, I think, that they used acoustic bullets. And so you could basically send very high energy pulses deep into the tissue. You basically line up steel balls and propagate ultrasound through it.
Anyone want to comment on that before we go on to another question? Pierre, do you want to say anything? No? Okay.
So if I understood you, you're saying that what people experience in some of these is changes in mood, and that's with like surface cortical stimulation. But my understanding is that there's no obvious way that like focal cortical stimulation would cause an overall change in mood, unless maybe it's
So
sort of back propagating activation of like some neuromodulatory system.
Well, so in that particular paper, they scanned the ultrasound, so it was not in one particular location, right?
So
what we're
like
doing is in one
cortex
location.
isn't mostly about mood, at least in I mean, not that anyone really knows, but
I mean, so there's interesting things that happen with our brains that people don't really pay attention to. So like when we do TDCS, right, you can get changes in mood, and I'm convinced that most of the changes in mood are just because you're passing electrical current in the skin, right on the head. And that's just, it's a different sensation than something you've experienced before, right? And that changes arousal, you know, there's all types of hormones that are going off and neuromodulators. And so I think that we have to be very careful when we infer that the effect on mood is really due to the ultrasound in one particular location, or if it's the whole sensory experience itself, right?
Yes.
What was the power density of the ultrasound at the focus spot to get the stimulation?
We couldn't measure it in the brain, but we estimated it based on our transcranial mapping experiments. It was what's called the ISPPA, which is the spatial peak pulse average intensity, was 5 watts per centimeter squared.